Yes, ma'am. If I'm actually might know more. Actually, I'm gonna.
So, where we had left off, we had just talked about solving exponential and logarithmic functions. We've been talking about logarithms. We're going to look at some more application problems here, and then start talking about financial mathematics as which will be our final section, chapter 15. We'll probably finish up chapter 15 next class. Then we'll have a review day and maybe the test. Well, either end of next week or beginning of the week after, or something like that. That's kind of what we're looking at. All right. So one application for these exponential and logarithmic functions would be with sound intensity. We measure sound intensity with the unit decibels. And the formula to calculate that sound intensity, or the number of decibels, is beta equals 10 times the log of I over I naught, where I is the sound intensity measured in watts per meters squared, and I naught is a constant, so that's always 10 to the negative 12 watts per meter squared. So we're told that the sound intensity of busy city traffic is approximately 10 to the negative 5th watts per meter squared. What is the measure of busy city traffic in decibels? So this is our I, and we know that I naught is always this. So there's me filling things in, right? What do I do at this point? Yeah, I could just type in my calculator, right? Or I don't really need a calculator to do this one. What is 10 to the 5th divided by 10 to the 12th? 10 to the 7th, right? Because the base stays the same when we subtract the exponents. Negative 5 minus a negative 12 is positive 7. And I remember that log, if I don't write a subscript down there, I remember the base is 10. So log base 10 cancels with exponent base 10. So I'm left with just 10 times 7. So I'm left with 70 decibels. Where do you guys hear the term decibels used most often? You guys watch live sports? When they almost always they have like the stadium noise meter, right? When it's like a big game or something, it's like, oh, it's as loud as a jet taking off in there, you know. Anyways, that's the gist. What?
What's a lot of decibels?
Well, I mean, 70 is pretty loud. That's like busy traffic. I'm guessing. I don't know. Let's look. All right, let's see. A whisper is 30. Loud noises above 120 can cause immediate harm to your ears. Motorcycle is about, engine is 95. Does that do it for you?
Yeah.
All right. Just a little quick Google. Yeah, there's nothing wrong being curious. I do that like probably 12 times a day. I'm like, I wonder what that is. Google. Imagine how hard it was to figure that stuff out before. What did we do before having a cell phone in our pocket? You had to look stuff up. You had to go to the library. Or get your encyclopedia at home. People used to have encyclopedias in their house. All right. The next scenario is the Richter scale. Do you recognize that? Earth science peeps. What do we use it for? Measuring earthquakes. Yeah. So the Richter scale is designed to measure the magnitude of earthquakes. The magnitude of the earthquake is represented by the letter R and can be found using the equation log of A over T plus B, where A is the amplitude in micrometers. So that would be like how much up and down distance the earth is being displaced, because that's like what happens with an earthquake, right? Like you have a fault and it like it slips and then it has to come back and it kind of like and then the T is the period of the associated wave in seconds. So remember back from last semester, the period would be if like this is the start, so it slips down, comes back up, and returns. The time it takes to do that is 1 period. Everybody's okay there? That's what we mean by a period. And B is a constant that accounts for the weakening of the wave with increasing distance from the epicenter. So if there's an earthquake that happens in Los Angeles, are we going to feel anything here? No, right? And the further away you move from that epicenter, the weaker the earthquake's going to feel. So like if the earthquake happens in San Francisco and you're out at like, you know, like an eastern suburb, you may not feel it much at all, right? May just like, oh, like something tipped over on my table. Meanwhile, it's like pandemonium near the coast or whatever. The reason we have that correction factor here is that most times earthquakes are measured. The measuring tool isn't right at the epicenter, right? That we've like empirically collected data and used it to kind of create a correction factor for saying, oh, the measuring instrument that measured this earthquake was like, 27 miles away from where the epicenter was. Like, so how do I correct the intensity that I felt here for like how bad it was actually at the epicenter? Hi, one down.
One down, there you go.
Thank you. Does that, you guys, kind of make sense to you guys as to what that B is doing? Okay. So the infamous San Francisco earthquake had a Richter scale measurement or scale magnitude of 7.5. How many times more severe was the most severe earthquake ever recorded? The 1960 Chilean earthquake that had a Richter scale magnitude of 9.5. So what we'll do is we're going to say, okay, well, I have two separate earthquakes. So I have, like, I'll need two separate earthquake equations, right? And it should seem pretty clear that, okay, well, I'm going to put 7.5 in here, and I'm going to put 9.5 in here. And what we're interested in is, like, how much more shaken was the 9.5 doing than the 7.5. So we're going to want to be comparing the A1 to the A2. See how much more up and down the A2 was than the A1. Everybody's cool with the plan? Seems like I have two equations, about 6 different variables. That's kind of a problem, right? But maybe not so much one. So let's think about this. what I'm going to do is I'm going to subtract the two equations from each other. So if I call this like equation A and B, and let's do actually equation B minus A. I have to make myself some room. So if I do that, I get 2 is equal to log of A2 over T2 plus B2 minus log of A1 over T1 plus B1. So far, so good. I'll distribute that negative sign through. Stupid machine. It's so frustrating sometimes. So I have that, right? After I distribute the negative sign through. Now let's think here for a moment. Mr. Kulik's going to argue that B1 and B2 are equal. Why would I argue that? Here's my argument, right? That B is a correction factor, correct? So because we've already have the magnitudes of the earthquake, whatever correction factor that needed to be applied was applied, right? So I can essentially assume that they're both 0, and I can just they can subtract each other out and they're gone. Or you can assume they're the same, in which case subtract them away and they're gone, right? Since one's positive, one's negative. Now I'm going to use my properties of logarithms, right? Because I notice I have the subtraction of 2 logs. What property of logarithms can I use there? The division property or quotient property, right? So that's going to be log of the positive piece divided by log of the negative piece. And I know to divide 2 fractions, that's the same as multiplying by the reciprocal. So I have A2T1 over A1T2. Everybody's okay there? Now, remember what T is. What is T representing? The period, which is a time, right? Do you think that the amount of time it's going to take for the Earth to do this, and back to here is going to be a long time or a very little time? It's going to happen really fast, right? So fast that, even though those are different periods, they're close enough to being the same. And if they are basically the same, or really close to being the same, can't I just do that? If T1 and T2 are about the same, then I can just cross them out. They'd cancel each other out. Does that feel all right? It's a little hand wavy, but it's okay. Particularly for a problem where we look at it and it's like, Mr. Kulik, there's no way that I have enough information to solve this thing out. So now I have this. 2 is equal to log of A2 over A1. How do I get rid of the log there? It's going to cancel out the log. So yes, that's log base 10. So what do I have to do to both sides to get rid of that log there? So it's not so it's an exponent base. So I'm going to do 10 to the second equals 10 to the log A2 over A1. So those guys go bye-bye. So what we're seeing there is that the Chilean earthquake was 100 times more like vertical displacement than the San Francisco earthquake. It's a whole lot of shaking going on. Does that feel okay? This was tricky because there's a lot of like, what is this thing representing? And I'm using kind of what it represents to do some hand wavy canceling out. But more or less, you're just plugging stuff into a formula and pressing enter, right? A third application, pH. Chemistry students, you know what pH is? Measurement of acidity for a solution. That acidity measurement is based on the number of, or the concentration of hydrogen ions in a solution. We usually, in chemistry, measure that in moles per liter. AKA, what do we call that in chemistry? Moles per liter has a special name. It's molarity. Molarity is what you called that. The formula for pH is that the pH of a compound is equal to the negative log of the hydrogen ion concentration. Typically, you measure solution or pHs from 0 to 14. 7 is considered neutral. That's the pH of like deionized water. Low pHs are acidic and higher pHs are basic, where 0 is the most acidic and 14 would be the most basic. It says a really sour lemon is found to have a pH of 22, and a bottle of bleach is found to have a pH of 10.2. What are the hydrogen ion concentrations of the two ions? And then how many times greater is that of the bleach than the lemon? I probably mean lemon than the bleach, but whatever. So let's do the lemon first. So 2.2 is the pH. That's going to equal to negative log of the hydrogen ions. And I'm putting an L subscript down here for lemon. So how do I get the concentration of hydrogen by itself? Divide by a -1, right? And then how do I get rid of the log in front of that? Exponent base 10. And then that's moles per liter for my hydrogen ion concentration, right? That's it. Easy peasy, right? Bleach, we're going to do the same thing. So we have 10.2 equals negative log hydrogen ion concentration for bleach. I do the same thing. I'm going to get 10 to the negative 10.2. It's okay that I skipped some algebra steps there, since they're the exact same steps. You guys are good, right? A bunch of all-stars in here. All right. And then the last one wants to know how many times greater is the ion concentration in the lemon than the bleach. I don't know why that's got to be a typo. So I'm going to do my lemon over bleach. So I have 10 to the 8th. That is what? That's 10 million times the number of hydrogen ions in that lemon than the bleach. That's a lot of ions. Everybody feel okay there? No big deal, right? Fairly easy. Our most complicated formula is probably this one involving Newton's law of cooling. We use Newton's law of cooling to describe how the rate at which an object cools. So if you heat something up, depending on what the substance it is, it's going to cool at a different rate between two substances. The things that can affect the rate in which it cools is what the substance is made out of, sure, but also the temperature of the room or the surroundings even, like. So those are the two big factors here. So our formula is T of T, that's the temperature at some time T, like the temperature in the future, is equal to the temperature of the medium, that's the surroundings, whether that surrounding is just air, or maybe if you're like a medieval blacksmith and you just were pounding on your sword and you stick it in the cold water to do some annealing, that's what that process is called. That TM might be the cool water you're dipping your blacksmith sword into. You guys have seen that in a movie or something probably. T naught is the initial temperature, so that's like how hot you heated up your sword before you dunked it in the water. The E is that number, or that irrational number like 2.71, yada, 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 that we talked about earlier. The K is a constant that's going to be specific to the substance. So the K for a, steel sword is going to be different than the K for, like a cake in the oven or something. And then T is time. Typically that's going to be measured in like minutes or something. And it would be, the constant is built to match whatever the unit is on the time. So like those two things would match. So like if you're doing this, or T is in hours, your constant would be different than if T was in minutes, even though you might be using the same substance, because that constant will be set so the units match up. Does everybody feel okay with like what the symbols in the formula are representing? Did you like my medieval blacksmith explanation? Usually, like if you have a picture, it's like, oh yeah. Or the other explanation I like is the pizza rolls. You guys make the pizza rolls in the oven, and you take a bite, and it's just like the liquid lava pizza stuff just boils your mouth. Next time you make pizza rolls, maybe you could figure out the K and then predict how long it's going to take to cool your pizza roll. All right. Anyways, a hard-boiled egg is heated to 96 degrees Celsius, is placed in a pot of 16 degrees Celsius water to cool. After 4 minutes, the temperature of the egg is 45 degrees Celsius. How long will it take in total to cool the egg to a temperature of 20 degrees Celsius? All right, so let's start here. So we know this is a cooling situation because it talked about like this egg cooling down, right? So we know the formula to use. So this T naught is like our initial. This 16 is like our temperature of the medium because we're dunking it in that water. This is going to be like T of 4. So that's the temperature after 4 minutes. And then we're going to be asked to find the T of T when that is 20. We're going to ask to be, the time when it takes to get down to 20 minutes. What haven't we been given here? K. So what we're going to end up using is this stuff to solve for K. And then after we've solved for K, we can use that piece to solve for T. Is everybody cool with the plan? So it'd be 2 steps to do this. So our initial step, we're solving for k. We have 45 is equal to 16 plus 96 minus 16 e to the negative k times 4. Is everybody okay with that? To solve this, what can I do? And do a whole bunch of algebra, or what else will work? Graph it on my calculator and find that intersection, right?
Why is it 45?
Because that's the temperature after 4 minutes. So when T is 4, I know the temperature is 45.
Oh,
So that's going to allow me to solve for K, because now I have everything but a K, because I have a time and a temperature. So if I wanted to do this on my calculator, I can just type this in as it looks on my sheet of paper here. My virtual sheet of paper anyways. Okay. Now this K is a constant, right? I don't know what kind of number this is going to be. Typically, it's not a very big number. So I'm just, X is representing my K. So I'm just going to go X from 0 to 10. I don't think it'll be negative. The Y is going to be a temperature. So I know that we're starting out at 96 and then cooling down, right? So I'll go 96 to 0. I don't think that, well, really 16 is as cool as this thing could probably get, right? Because it's being dunked in a 16-degree thing of water. Everybody's okay there? But if you did 0, it shouldn't make any difference. So there's my cooling curve. And there's my 45 degrees. So the K was real small. That's okay. Second, trace, intersect command, enter, enter, enter. So the K was about 2.54. Yes, 0.254. Or if you wanted to solve this algebraically, I would subtract 16 from both sides. That's going to give me 29. And then divide both sides by 96 minus 16. That's 80. And then we'll do the natural log to cancel out the exponent base of e. And then divide that all by negative 4. And that should get me the same answer. Either way of doing it is okay. Just to show you that I get the same result. Pray that I did. I did all that algebra in my head real quick. But I think it's going to be right. Yeah. So far, so good. Now that we've solved for K, we can solve for T. So we're going to have 20 degrees is equal to 16 plus 96 minus 16 e to the negative 0.254 t. Feel good there, everybody? So if I do the same thing I did last time, I'd subtract 16 from both sides, divide by 80, do the natural log, and then divide by the k. Or you could graph it and find the intersection as well. Totally fine to do that. Again, what do you know about the t? It has to be greater than 4 at this point, but it's going to be some number, probably less than 20. That would be my suspicion. Considering you got most of the way there after 4 minutes. But you could do it this way as well. So 11.8 minutes. Or you could graph and find the intersection rather than solving manually. Either is okay. Does that look good to you guys? So far, so good? Not a big deal on these story problems. They're basically just like a solving problem that's easier than the solving problems I've given you already. You just have to do a little bit of setup. In section 15.5, we're going to be talking about financial mathematics, or we're going to start by interest calculations. So we'll start by talking about simple interest. So simple interest is like a made-up thing. Nobody actually earns simple interest anywhere. But basically the idea is that the interest is only paid on your initial investment. So if you invest $100 and you get a 5% return every year, the first year you get $5. Second year you get $5. The third year, still get $5. So that 5% is always based on the initial amount. Everybody's okay with that? So the formula we use there is FV is equal to PV times 1 plus RN over 100. So FV is the future value of the account. PV is the present value. That's your initial investment. R is the percent rate of change. That's the interest percentage you're earning. But it's written as a percentage. That's why it's divided by 100. And the N is the number of compounds that happen. So, if you're earning 5% for 5 years, the N is 5. If you're earning 5% every month for 5 years, the N is 60. 5 times 12. Everybody's okay there? All right. If you were to invest $2,000 at 6% interest rate, how much money do you have in the account after 3 years? That's it. It's like, whoop-diddy-doo, Mr. Kulik. And then it's just calculator time, right? So how much money did we earn in interest over that 3 years? $360, right? The $2,000 was our initial investment. The interest that we got paid was only the difference, the $360. Not bad for doing nothing, but now, again, simple interest is basically a made-up thing. Nobody actually gets paid in simple interest. Banks don't do that. Loan companies don't do that. Nobody does this. Maybe your neighborhood bookie does or something. The compound interest is really what everybody does. So in compound interest, the difference is you get paid your percent interest on the current balance in your account. So in the previous example, we invested $100 at 5%. If it's compound interest, the first year you get $5. The second year you're going to get 5% of $105. And then the third year you get 5% of the current balance again. And so each year you're getting paid a little bit more in interest, assuming you're not pulling any money out, right? Does everybody kind of get the idea? Think that's a big deal or little deal? The compounding. It makes an enormous difference over time. Over 100 years, you'd be shocked at the difference. So it's orders of magnitude. It's like being a multimillionaire versus having like $10,000 difference. All right. So again, it says if you invest $2,000, 6% interest rate, compounded, that's how you can tell the difference between the formulas annually. How much money do you have in the account after 3 years, and how much did you gain in interest? So it's asking for a future value of that account. Now the K here is a new parameter. That's the number of compounds in inside of 1 year. So if it's annually, just 1. If it was compounding monthly, the K would be 12. If it was compounding daily, 365. If it's compounding quarterly, How many quarters are in $1? How many quarters are in a year? 4. Still 4. You got if it's
So what does it mean by compound?
that's how often the interest is being applied. It's just that like when we're compounding, if you're getting like 6% annual interest compounded monthly, you're getting like 1/12 of that 6% is happening every month. So you're getting just like a little over the whole course of the year. That's what it's kind of happening. Is that?
Yeah.
Okay. So same situation, right? Just compound interest versus oops daisy 100 versus simple. What was the difference there? How much more money did we earn? $22.03 or something. Notice that I rounded that to 2 decimal places. Why 2 decimal places? Yeah, it's money. So, yeah, we round to the penny, right? Here's a story for you. If you're a bank, which way are you rounding?
Down.
Always down. If you have $139.42.9, it's 42 cents. If I owe the bank money, which way are they rounding? Always up. If I owe you $142.39 and then 1/10 of a penny, it's 40 cents. Do you think all those little tenths of a cent make a big difference or a little difference? It's millions and millions of dollars a year for a bank to do this. Millions and millions of dollars. Yeah. It's actually a plot point in one of the old 80s Superman movies, like maybe Superman 3. Is one of the villains like writes a computer code that just like siphons off all the tenths of cents that the banks are using. Yeah, I don't remember the whole. There's some nuclear plot in it also. It's a terribly like nobody under. I don't. It's a movie that makes no sense, but it's a thing. If you grew up in the 80s, you would have remembered that. And so, how much did we earn in interest here? You know, like. Yeah, something like that. Cool beans. So your K's, depending on the verbiage in your problem, you know, annually is K is 1, semi-annually K is 2, quarterly K is 4, monthly K is 12, weekly K is 52, daily K is 360. Just kind of grinding through a little bit of vocab. So sometimes we don't remember how many weeks are in a year or something. Like it's 52. We wrote it down just in case. All right. Suppose Gene invests $800 at 7% annual interest. How much will be in her account in 5 years if the interest is compounded annually, semi-annually, quarterly, monthly, weekly, daily? So I'm going to do this all in my calculator and we can just compare. Do you think this K is going to have a big difference or little difference? Big difference. Okay, let's see.
Wouldn't it be the same? Because at the end of the 5 years, still.
Well, the interest in the account, like the account value is going to be slightly different each time the interest is paid. So, like, it does make a difference. So I'm going to set this up, and we're just going to like change like one number each time. So this is annually. And then we have semi-annually, so the K just becomes 2. So I'm going to change that to a 2. Yep. Okay, so like $6. That's not bad. Okay, quarterly. Picked up like an extra $350. Okay. Monthly, that's going all the way to 12. Yeah, like less than $3. Well, at 52, that's like 5 times as many. That's gonna make a big difference, right? Let's see, monthly to weekly, 80 cents. 365 though. 365 is an enormous number, right? Quarter, about a quarter. So what's the takeaway? It's better,
It's good.
but like the number of compounds per year, it makes a difference. If you're talking about enough money for a long enough time at a high enough interest rate, sure, the better K is going to, helps, but it's not going to be like the driving factor, right? The driver is still the interest rate or the time. That's really the two things that make the biggest difference. All right. Let's say Mara has $1,000, puts in a savings account, 6% annual interest compounded monthly. How long will it take before Mara has $4,000? So FV, PV, R, and then K is 12, right? What are we solving for?
How long it takes.
Yeah, the T. So the equation we're going to write something like that. To solve that, what can we do? You could solve it using a logarithm or graph in our calculator and find the intersection. Let's do it that way. At least for starters, right? Just because if I have to use all those logarithms and stuff, like it's probably just going to be the same amount of time that it would take to do it graphically versus algebraically, and like I have much more confidence in not screwing something up just by typing in my calculator versus algebraing it up. You know what I mean, guys? I'm going to mess with my window here, though. So T is time, right? I don't really have any idea how long this is going to be, but I'm just going to say like 0 to 50. I'm hoping in 50 years we've doubled our money. Probably well in advance of that, but it's hard to guess from an interest rate. So I usually just, do bigger than you need. The Y minimum, well, that's going to be 2,000. That's the least amount of money we're ever going to have in our account. The Y max, well, I want it to be bigger than 4,000. I'm just going to pick like 8,000 or something. It doesn't really matter as long as it's at least 4,000. So here's my compound interest. There's my 4,000 line coming in sometime. There it is. Ooh, that happened real quick. Second, trace, intersect command, enter, enter, enter. 11.6 years. That feel okay to you guys? Okay.
What's like a normal interest?
Depends on if you're talking about on a loan that you're taking out or the interest rate the bank is paying you for your investment.
Like a saving account.
You're not getting 6%.
Low.
Yeah, probably between 2 and 3.
Like a loan would be probably higher.
Depends on how the state of the economy. So yes, and depends on what it's for. Like auto loans are often much higher rates than like a home loan, because it's pretty easy for your car to essentially lose all of its value. It's hard for the house, and the insurance people carry on their homes is vastly different than what they carry on an automobile. So like it's a bank risk thing. The current interest rates right now, like if you want to buy a home, you're probably looking at like 7 or 8%, which is pretty high, historically speaking. Like at the beginning of COVID, when everything was like locked down and interest rates were kind of cut to try to keep the economy going, you could probably have gotten something like in the 3 and 4 range, which is like, if you have like a $250,000 note on your house, it's probably like $80,000 over a 30-year mortgage. The difference between like your interest rate now and your interest rate then. So it's probably several $100s a month on your mortgage.
So I mean that you gotta pay.
You pay more
Yeah.
for your house because you're paying this interest rate. But you can always refinance later and get a better interest rate. All that tax on more time you have to pay. But all right. Next one. So Gwen has $600 in a savings account. What annual interest rate would she need if we're compounding weekly and she wants to have $1,500 in 10 years? So this is my present value. This would be my future value. That's my T. This is my K. And then we're solving for the R. I just want to call that I. So 1,500 equals 600 times 1 plus R over 100 times 52, 52 times 10. Everybody's okay there? So again, I'm going to do this in my calculator. I could do it by hand also. This one would just involve using like a square root. Well, not a square root, like 520th root. But again, like I'm just going to do it on my calculator. So in this time, X is representing an interest rate as a percentage. So I'll go, 0 to 20. 20% interest rate would be absurd. Nobody's getting a 20% interest rate. My Y min should be 600. That's the least amount I'm ever going to have in my account. My Y max needs to be bigger than 1,500. I'm just going to make it 2,000. That ought to do her. So again, here's my compound interest curve. Here's my 1,500 line somewhere. Oh, did I not put it in? Oh, I forgot to put it in. There we go. So there we are, second trace, intersect command, enter, enter, enter. So 9.17% interest. Good luck getting that there, Gwen. Maybe if you have like, if you're doing like a stock investment, maybe you can get 9% return on something like that. That's it for today. This feels like good enough. So we're adding 131 to 146 to the problem set. Again, this Sunday, all that's due is 37 to 130, and then the delta math. This stuff that we assigned here today would be going into the following Sunday's problem set. I'll get that into my Notre Dame so you guys can see that stuff. Sound fair? Everybody happy?
Yes.
I mean, relatively speaking, you're happy to end after an hour or so today.